First, what we're going to address is just the question of what is a function. And this might be, again, like I feel like a big theme of this course is, we're going to talk about some things that you already have seen before, right, in high school and stuff like that. And you might think you know, but you probably don't know it in such a rigorous way, right? I don't know how you guys learned about functions, but when I learned about it in high school or something, I learned about it like it's kind of like a machine for turning an input into an output, which is not a very good description really, but it kind of does the job most of the time, right? And I mean, at least from high school or something, you're probably most familiar with functions where the input is a number and the output is some algebraic expression involving that number. So you're probably most familiar with, cases where the input is a number and the output is an algebraic expression of that number, right? So things like, f of x is x squared, f of x, even more complicated things like e to the x squared plus sine x, or f of x log base 10, absolute value 1 plus x, right? I mean, these are just random functions, more or less. I don't know, am I sort of right that this is the sort of thing that you're pretty used to? Yeah. So something to kind of, maybe this is not like that big of a jump, but what you should get used to for the purposes of the rest of this course is the idea that, for a function, the inputs and outputs don't have to be numbers. So in general, for a function, they don't have to be numbers. And secondly, if you have a function, it's not necessarily the case that you can write your function as a nice algebraic expression. So the function, a function may not have a nice algebraic formula. However, this basic idea that a function takes inputs and turns them into outputs, that's still true, okay? It's just that the kind of mechanism for turning your input into an output, it doesn't have to look like this, right? It doesn't have to be some formula. But still, the concept of every input has a unique output, that's actually what really defines a function. Okay. Any questions about this so far? I haven't really said anything, but okay. Yeah.
When you have periodic functions where different inputs with the same output?
Yes. So I said something like the word unique here. What I mean by that is, so you can have the same output produced by two different inputs, but each input should have a unique output. Like if I plug in, if you take one of these, for example, if I take f of x equals sine x, that's periodic, right? If I put in a value for x, only one number pops out. That's all I really mean. Every number has one output. Each output could come from two inputs. It could come from infinitely many inputs. Okay. Yeah, so regarding this, yeah, so what I'm saying, I guess, is, yeah, you kind of know what functions are, but you might not know exactly what a function is. In particular, you've probably never heard that a function is a relation. So that's how we're going to talk about functions. So a definition. So let A and B be sets a function from A to B is a relation f, so from A to B, so when we have a relation from A to B, that's the same thing as a subset of A cross B, such that for every, so you should think of A as being like the possible inputs, right? And B as being the kind of outputs. And so what I've been kind of saying is that every input has a unique output. So for every A in A, there is a unique B in B such that the pair AB is in the relation F. Okay. So yeah, you should think of a function as indicating a relationship, right? Every input is related to its output, kind of thing. Okay. So for example, if I take the function, so here we've got the function f of x equals x squared. As a relation, you would think of that function as being the set x squared, such that x is in R, so which is a relation from R to itself. Okay. But yeah, we can talk about this more in a second. Okay. Okay, so functions are relations. We need some more notation and terminology here. So the notation for functions. So if I write f colon a arrow b, slightly annoying notation because actually we've used this colon for something else in set theory notation, and we use the arrow for logic stuff. But yeah, we're reusing these symbols for a different meaning now. So if I write f colon a arrow b, so this just translates in English to like f is a function from A to B. Okay. Any questions about this so far? Okay, another definition. So given a function from A to B and an element of A, so we define, okay, because this is a function, for every A in A, we know there's a unique B such that AB is in F. So the unique B in B such that AB is in F is called the image of A under F. And a bit more notation. So if I write f of A equals B, that just means that B is the image of A under F. So it means B is the image of A under F. I mean, yeah. Okay. So, okay, I mean, this is the way that you're used to writing functions. And I guess what I'm saying here is you can still write functions in this way, right? Where you write f of x equals x squared. Like, that's a valid kind of definition of a function. But yeah, but what it really means is that the image of x is x squared. Okay. So let me give some more definitions, and then we'll look at some examples, and hopefully it'll become a little bit clearer. So if f is a function from a to b, we call a the, so probably you're aware of this terminology, so the domain of f. So the set of possible inputs is the domain. Some terminology you might not have heard, though. So you might be expecting me to call B the range, but it's not the range. So we call B the codomain. Okay, so yeah, so I mean, you may have also heard of something called the range of a function, which also makes sense. So the range so the thing about the domain and codomain is that so when I specify a function, so you don't have to, so everything in the codomain doesn't have to be the image of something in the domain. So for example, if I define, a function from the reals to the reals such that f of x equals x squared for x, if I look at the number -1, -1 isn't the image of anything because there's no real number that you can square to get -1. So the way the range comes in is the range is all the things in the codomain which are actually images of something in the domain. So the range of f is the set f of a such that a is in a. And the notation we'll use for this is kind of Rn. I think this is what they range like this of f. So let's, maybe look at some examples. Were there any questions about these definitions? Okay, so so often, so maybe I should say that, often the simplest way to define a function. So you should you should be aware that a function is a relation. So a function is a set, right? It's a subset of A cross B. But at the same time, it's not always the easiest way to define the function. So sometimes it's easier just to say what is the image of each element of the domain. So often the simplest way to define a function is to specify the image of each element of the domain, rather than writing the function as a set. Okay, and this is the thing that you're kind of used to, I think. So this is a perfectly valid way of defining a function. So let f be the function from R to R such that f of x is x plus 1 squared for all x in R. Okay. So this is like I said, this is a valid way to define a function. But equivalently, if you want to think of this as a relation, this is the same as the set of all pairs x comma x plus 1 squared such that x is in the reals, which is a subset of R cross R. So what I'm saying is writing f equals this is the same as writing f of x is x plus 1 squared for all x in R. Any questions about anything so far? Oh, yeah. So here, I would say the domain is R, the reals. The codomain is also R, the reals, because, I mean, to figure out what the domain and codomain is, just look at the function definition, right? R, you know, the domain is the reals, the codomain is the reals. That's how it was defined. But what's the range? Well, in some sense, okay, in some sense it is the set of all x plus 1 squared for x in the real numbers. But there's a kind of more concise way to write it. But that, I mean, that is, like technically that's right. Just to write, I mean, this is a perfectly valid way to write the range. I mean, this is by definition, you know, that's what the range is, right? But what if I tried to kind of simplify this and write it another way? Yeah, pretty close. I think you, oh no, you're right. My bad. Yeah, it's going to be, oh no, sorry, I screwed up writing this. Yeah, it should actually be 0, but yeah, there wasn't supposed to be a squared there. But yeah, so technically I could set x equals -1, I could get 0, but you can't get it anything less than 0. So this is going to be the set of all x in, or let's say y in the reals such that y is at least 0. Right, so it's all the non-negative real numbers. Okay, because if you square a real number, it's always non-negative. So you can't get -1, for example. Okay. Okay. Another way to say this set, by the way, I don't think we've really talked about this interval notation, have we? But have you guys seen this kind of notation before? Okay. So it's a set of all, this says the set of all real numbers between 0 and infinity, obviously not including infinity, it's not a number, right? So maybe, I mean, in case anyone hasn't seen this, let me just quickly write down how it works. So right, so if I have like open brackets a, b, that's the set of all real numbers such that it's, you know, x is between a and b. If you write closed brackets, square brackets, that's the real numbers between a and b inclusive. And if you mix them up, then basically like this is a perfectly valid thing to write. It just means that like you have to be strictly bigger than a and less than or equal to b. So it's x in R such that x is bigger than a, less than or equal to b. But then when you involve infinity and stuff like that, right? So this will be x in R, x at least 0. And I would suggest pretty much, I mean, in almost any circumstance, don't write a closed bracket with infinity, right? I mean, unless somehow your function is being, or you're doing something where it's defined on all numbers plus infinity or something. But like, infinity is not a number, so yeah. So usually we don't want to include infinity. Okay. So, okay, any questions about anything so far? Or is this all good? Yeah? We haven't done any such examples, have we? So we can do an example. But yeah, so this I'm only really talking about this in the specific context of things involving real numbers. So this is just some notation for real numbers, sets of real numbers. Yeah.
Is there a name for this kind of notation?
I guess probably interval notation. Maybe. Because here we're talking about, you know, intervals of real numbers, like kind of, yeah. Was there another question? Okay. Yeah, this is just a useful way of representing certain sets of real numbers, basically. There's nothing really, yeah, so it is quite special to the reals. Okay, so I mean, maybe we should talk about at least one example where the inputs and outputs aren't numbers. Since I said that they don't have to be numbers, we should look at an example. So one kind of, I don't know, silly example, but suppose I let A be the set of all students at UVic. I let B be the set of all courses. And I let f be the function from A to B, such that f of x, so for each student x, f of x is student x's favorite course, right? You're only allowed to have one favorite, okay? If something's your favorite, it's your very favorite. So this is a function, right? Because every input has exactly one output. Of course, like, f of u is math 122. Okay, probably not, but so is the kind of the concept here. This is a function. The inputs are students. The outputs are courses. They're not numbers, and that sort of thing. And there's no formula for this, right? I don't have a formula which, if I input a student, it's going to nicely give me their favorite course, right? Yeah. So right. So it couldn't output like a list of 4 different courses or something. However, you could say so that would be bad with this domain and codomain. So if my codomain consists of single courses, you can't output more than one course. However, what if I took the function where the codomain is the power set of this set, right? So if I took so let's say I call it G from A to the power set of B, where B is still courses at UVic, I could say G of X is the set of all courses that X is registered for, right? So, G of U might be math 122, I don't know, math 109, I don't know, okay, maybe nobody has exactly these courses, but maybe there's somebody called Bob in another section, and they're taking these 2 courses. Right? But this would make sense. So here I'm not saying that the output is 2 courses. I'm saying it's a single object, which is a set consisting of 2 courses, and that's okay. But that's a good question. Is it clear what the difference is? Right? If I tried to define this as a function from A to B with this property, that's not valid, because this is not an element of the set of courses. It's an element of the set of sets of courses. Anyway. Okay, so a few more definitions, or at least one more definition. So we've been talking about images and the fact that every input has exactly one image. But actually, this question about periodic functions came up. So for certain things in the codomain, it may be the image of many different things. And there's a kind of name for that, well, for saying what something, well, anyway. So given a function f from A to B, and an element b, little b, in big B, we say that some element little a of big A is a preimage of B if B is the image of A. So if f of A equals B. Okay. And a key thing here is like this word, a preimage, right? So I'm not saying it's the preimage of B because it might not be unique. So the preimage, preimages are not unique. And moreover, preimages might not even exist. Like a preimage, and they need not even exist. What I mean by that is if I take, if I use this picking the favorite course example, maybe the preimage of Math 122 doesn't exist. Maybe nobody would pick this as their favorite course. But okay, maybe a kind of more numerical example. If I take this again, it's important what I pick as my domain and codomain. So again, if I take f from R to R, such that f of x is x squared for all x and R. So the number, if I take the number so 2 is a preimage of the number 4, right? Because f of 2 is 4. But negative 2 is also a preimage of 4. Because f of negative 2 is 4, right? But also, negative 1, has no preimages. Right? Because there does not exist x in the reals such that f of x is negative 1. Right? There's no way to square a number and get a negative number. And that is something, that is kind of, getting ahead of something I wanted to actually say. If you change the domain and codomain, that changes the preimages, right? But so negative 1 has no preimage. If I take 0, has only one preimage, which is 0 itself, right? Because 0 squared is 0, but you can't get 0 in any other way. Yeah, f is a function from the real numbers to the real numbers. Yeah, totally. Yeah. So I've just been kind of dealing with these kinds of examples, but we'll do more examples, and yeah, you totally don't have to always have the same thing on both sides. In particular, here's an example, right? Courses and students are different things, and we're mapping from courses or students to courses. That's a good question. The thing is, if I define some very abstract, weird function, you might not even, by kind of thinking about that function, you might not even be able to figure out what the range is. In which case, it becomes hard to even define what the function is. So this is sort of, it makes life easier to have a bigger codomain. So you just define sometimes you want to define the domain and codomain to be whatever makes sense, and the easiest thing, and then, because it may not be easy to find the range. It might be actually very difficult. So you can, for example, if we go back to this one, if we pick, so courses are never students, right? But if I pick a course, pick this course, it might have a preimage. There might be somebody who this is their favorite course, but so that doesn't, so the fact that courses are not students doesn't mean that they don't have preimages. You might have to, right? Because, well, the thing is, whenever I take an input, the output has to be in the codomain somewhere. So, yeah, we'll look at some examples like that. But let's just, to be safe, let's say we take the same function, but we change both the domain and codomain to be the complex numbers. So now negative 1 has 2 preimages, even though it had 0 before. which are I and negative I. Okay, and actually, now everything's going to have a preimage, actually, it turns out, I think. Yeah. Yeah. What'll happen is you won't even have a function anymore. Yeah. So maybe let's do one example like that where I'll show the kind of difference between these things. So, for example, if I take, I'm going to write down allegedly 3 different functions. So suppose I take f from what did I want to do? Reals to the reals, okay, boring one, such that f of x is x for all x in the reals. Now I take let's kind of mix it up a bit. So suppose I take g from the integers to the reals, but it looks like the same function, right? G of x is x for all x in the reals. And now I take h from reals to z, h of x equals x for all x in the reals. Or sorry, x in, sorry, I'm messing these things up. We should always be talking about x being in the domain. So that one should be z. Yeah, I mean, there's not really a good reason, to be honest. So I guess for the purposes of this course, there's a lot of things we make you guys do, which are just to show that you understand the concept. So I mean, if a mathematician was writing something and they said f of x equals x for all x, I would know, okay, they mean all x in the domain, of course. But for your guys' purposes, you should probably make it clear that you understand x is in the domain. But kind of like how I messed up here, where I wrote x is in the reals. Yeah. Okay, so so allegedly these are 3 different functions, or these are 3 functions. They all kind of look the same, right? They all just have f of x equals x, g of x equals x, h of x equals x. So the sneaky thing is, though, the third one's not a function. So h is not a function. Okay, and the reason is that if I take, let's say, h of 1/2, I'm supposed to get a half, but 1/2 is not in the codomain. So 1/2 is not an integer. So every input should have an output that lives in the codomain. Like, it has to be an element of the codomain. This input has an output, but I mean, it's not in the codomain, so this is just not a function at all. This is just, like, sort of writing this third line here is kind of nonsense. I mean, it just isn't a thing. Now, f and g, those are okay. So these are both functions. But something to be careful about is that they're not the same function. Even though they sort of do the same operation, they're not the same function because they don't have the same domain. So f and g are functions, but not the same function, even though they look the same. So let me just quickly address what it means for 2 functions to be the same. So for 2 functions, f and g, so if we write f equals g, so that means, so I'll just write f equals g if and only if they have the same domain, same codomain, and they've got to be this. They've got to do the same operation. So every input goes to the same output, or in other words, f of x equals g of x for all x in the domain. Okay. So these two functions here, they kind of satisfy two of the requirements. They've got the same codomain. They do the same operation, right? Each input that's valid for both of them, they do the same thing. But the problem is they have different domains, so they're not the same function. Okay. So also, if I was to have two functions that look the same, and I change their codomain, so if I take, a function j from the reals to the complex numbers, where I say j of x equals x for all real numbers x. This would, again, it looks like the same function as all of these ones, but it's, again, a different function. Even though it has the same domain, or it's different from f, for example, it has the same domain, it does the same operation, but the codomain is different. So we would say these are different functions. So f is not the same as j. If you change this to the natural numbers, that would be fine. Also, if you change it to the integers, it'd be fine. But yeah, as long as you change this so that, if you shrink the domain a bit so that everything actually does map to an integer, you'd be fine. So even if I change the domain to the set, the set 1, that's going to be a pretty simple function now. It just maps 1 to 1, but that would work, right? For this example, but generally, no. So for example, if I take f to be the function from the reals to the complex numbers, where I take f of x is, I just take the real number x and I multiply it by I, where I is square root of -1, then now your codomain is definitely not a subset of the domain. Or if you want to go the other way, if I take the real, from the reals to the integers, and I take f of x is the floor of x. Now we've got so here we've got a set from a smaller set to a bigger set, and here we have from a bigger set to a smaller set. So they don't have to be subsets of each other or anything like that. Well, in this case, it kind of is, because this function is trying to say that a half goes to a half, but a half is not there. If you were taking, say, the floor function or something like this, then that would make it a function. But yeah, the output has to be an integer. So the problem is that the outputs aren't integers here.